All right, let's talk about nuclear physics and the Standard Model. In order to understand the Standard Model of physics, we need to kind of describe what we already know in terms of the atom. And that is this little box right here. We know the atom has a nucleus, and inside the nucleus contain the protons and the neutrons. They're referred to as nucleons. They're the particles that are in the nucleus. Protons have a positive charge, neutrons are neutral. They're both very massive and almost equally massive. Not quite, neutrons are a little bigger, but completely way more massive than electrons. Your electrons are not nucleons because they are not found in the nucleus. They're the ones that are outside the nucleus. They're negatively charged, and they're really, really tiny. Another thing that will come into play when talking about the Standard Model, or really more or less explaining some terms that go with the particles, is understanding E equals mc squared. Now, a lot of you have heard of this before. If I were to ask many human beings what they think of when they think of Albert Einstein, they think of E equals mc squared. That doesn't necessarily mean you know what it is. A lot of you probably have never even thought about what it means. And so in '05, Einstein kind of came out with this whole theory of relativity and a bunch of other stuff involved. All kinds of great physics he's attributed to. I can't go into the relativity aspect, but part of that relativity aspect is where he developed this relationship of mass and energy. And what he suggested and was able to show later on, but very accurately, that mass and energy can be considered equivalent. We can tell you how you can estimate or calculate how much energy a particular, say, ball of material has if it were to spontaneously turn into energy, and vice versa. If energy were to turn into matter, we could calculate how much matter it'd be equivalent to. This isn't really important in a regular day scheme of things in physics, but when you get into particle physics or when you get into quantum physics, it really does come into play because kind of like relativity in terms of am I moving or is the thing next to me moving? Similar here. Is it mass? Is it energy? It's kind of both, and it can be described as both. So let's talk about that a little bit more. So let's look at these particles, protons, neutrons, and electrons, right? Symbol for a proton is P, the symbol for the neutron is N, the symbol for the electron is E. We can talk about their mass. They're all really tiny, 10 to the negative 27 for protons and neutrons. Even tinier for electrons, 10 to the negative 31. Those are really tiny values. So we've got two ways in which we're going to now replace this mass column. Instead of referring to protons in kilograms, we're going to either refer to them in atomic mass units or in terms of their energy equivalents. That's that E equals mc squared part. I'm going to come back to this column in a second. Now, these numbers don't exactly match the New York State reference tables. These numbers in this slide are more accurate than New York State reference tables. The reference tables will round or estimate, and I'll refer to that again in a moment. So let's look down here now. A unified atomic mass unit is represented by U. Now, if you were in chemistry or you've taken chemistry or you're going to take chemistry, they tend to just refer to it as an AMU, an atomic mass unit. It's the same thing, okay? We refer to it as a U. They refer to it as an AMU. It's really no different. And one atomic mass unit is 1.6605 times 10 to the negative 27 kilograms. It's really tiny, and it's also really close to the mass of a proton or a neutron. It's based off of this interesting standard. It's actually 1/12 of the mass of a carbon-12 atom. If you have no idea what I'm talking about there, not a big deal. If you took chemistry, you'll understand that this is an isotope of carbon. It's a very stable isotope of carbon. That's why the standard was created. Not a huge deal that you don't understand that part right now. We can also refer to an atomic mass unit's energy equivalents. And that's where we basically start to take mass and energy and think of them as the same thing. And if we were to take this and plug it into E equals mc squared, we're going to write in 1.6605 times 10 to the negative 27 kilograms times the speed of light squared, which is 3 times 10 to the 8. We're going to square that number. You're going to get a number not exactly equal because there's rounding issues here, but really similar, really close to the energy equivalents, but in joule form. And I'm going to write that down to this math for you here. It's going to be relatively close to 1.5 times 10 to the 10 joules. Now, that's not exactly right. I've rounded, but it's very, very similar to that. Now, if you recall, and even if you don't, it's on the front page of your reference tables, we can convert joules into electron volts. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. An electron volt is the amount of energy required to move one electron through 1 voltage of potential difference. It's helpful to refer to really tiny energy values in EV, so we don't have to continuously write out these awkward scientific notations. So if I take this number in joules and divide by that 1.6 times 10 to the negative 19, I will get a number very close to 9.31 times 10 to the 6 electron volts. It's not exactly. I've done some rounding here. This is what we're going to refer to as the mass energy equivalence of one atomic mass unit. 10 to the 6 stands for million or mega. So you also will see this written as 931 mega electron volts. I apologize here. It's not 9.31 times 10 electron volts. It's 931 times 10 to the 6 electron volts. Let me fix that. So, anyhow, if this was way over your head, it's really not the end of the world. This is on the front page of your reference tables. And this is the mass energy equivalence of 1 U. So if we want to refer to as a U in this awkward mass in kilograms, we would use this number. But unawkwardly and more acceptably, we're going to use this number, 931 mega electron volts, which is really 931 million electron volts, or 931 times 10 to the 6 electron volts. When we talk about it in terms of protons, neutrons, and electrons, well, a proton and neutron are very close to 1 U. Not quite the same, but very, very close, with a neutron being a little bit more massive. An electron is significantly smaller than that. In terms of their mass energy equivalence, we're going to say that a proton is right around 938 mega electron volts. A neutron is 939 mega electron volts, and an electron is actually about half of that, or half of 1 electron volt, 0.511. I need to start getting into the standard model, which is the more accepted model of the atom. It talks about what not only is the atom made up of, but what are the things in the atom made up of. Before we get there, I got to talk about 2 new natural forces. Now, we've already learned 2. We've learned about gravity, and we've learned about the electromagnetic force. Those are 2 of the 4 fundamental forces in nature, which means all of nature is governed by one of these 4 forces. The strong nuclear force and the weak nuclear force are the 2 new ones, and that will complete your 4 fundamental forces. Your strong nuclear force is indeed very strong. It is the strongest force in all of nature. It's about 100 times stronger than the next strongest force, which is the electric force. Problem with the nuclear force is it's got a very, very, very tiny range. It can only exist within the nucleus of the atom. So that means anything outside of the nucleus, such as electrons, will not interact with the strong nuclear force. The strong nuclear force, more or less, is responsible for holding the nucleus together. It allows atoms to become stable. Otherwise, the electric force will have them rip apart because protons don't like to be near other protons. The other nuclear force is the weak nuclear force, and as you can expect, it is weaker than the strong nuclear force. Not only that, it's also weaker than the electromagnetic force. It's a relatively weak force. It too has a very limited range, and it's approximately the range of the nucleus. It's actually a little bit larger than the nucleus. Just by a little bit. Electrons can and will interact with the weak nuclear force. And it's primarily responsible for nuclear decay. Now, we won't be covering nuclear decay in our class any more than understanding that the weak nuclear force is what is responsible for nuclear decay. The biggest one that we are going to be talking about today is the strong nuclear force. So I have this little table down here that helps us rank it. Strong is the strongest. Then we have EM. Then we have the weak. And then by far the weakest force is gravity. If you look at these numbers here, if we were to put electromagnetic force as a value of 1, the strong nuclear force is 100 times stronger. The weak nuclear force is 10 to the negative 5 times weaker. Now look at gravity, 10 to the negative 43. It's so many factors weaker than the strong, the EM, or the weak force. It's incredibly weak force. Very easy to overcome gravity. We overcome gravity all the time. We lift our legs up and walk. Whereas protons, it takes a whole lot of force to rip them apart from each other in the nucleus. The rest of this stuff you don't need to worry about. Okay. Last thing I want to show before I get into the standard model is this interesting little chart that kind of explains if you took chemistry, and this isn't the end, it's not an end all to understand this unit if you haven't taken chemistry, but if you have taken chemistry, you're going to learn that as the atomic number increases in size, atoms need more and more neutrons than they have protons. Early on, atoms have the same number of protons as they have neutrons. Once they get bigger, they require more neutrons than they require protons. And this is all about stability. And the reason for it is that the number of protons, as it gets bigger and bigger and bigger, they want to pull each other apart because protons don't like being near each other. So if I have a ton of protons, there's going to be repulsion that's extremely large. And understand that strong nuclear force is what's keeping them in. But ultimately, you get to a scenario where there are just too many protons. So to balance that out, we need more neutrons. And those neutrons really will act as glue. They help counteract that electric force because the strong force will also pull them in. And it's all about stability. It's the most I'm going to talk about that. Just want to bring it out because I think it's interesting. It's all in the nucleus. All right, antiparticles. What the heck are antiparticles? I could go on and on and on about antimatter, talking about the universe, talking about all kinds of cool scientific experiments, talking about particle accelerators. For the most part, I'm going to stay away from that. Probably talk about that in class. But antiparticles are simply particles that are almost considered opposite of regular particles. For every normal particle, there is an antiparticle. Take protons, for example. We have protons, and then we have antiprotons. What does that mean? Well, an antiproton is just like a proton. It's got the same mass, it's got most of the same properties, with two major exceptions. We'll have opposite charge, so a proton is positive, therefore an antiproton is negative, and it'll have opposite magnetic moment, or opposite spin. This magnetic moment and spin bit helps explain a lot of stuff in chemistry about how the atom is arranged, and it even explains how it creates its own magnetic field. We're not going to really address it so much about what it is. Just understand antiprotons have opposite spins. So for example, if a proton has one set spin, an antiproton has the opposite of that. So just to recap, all antiparticles are the same as their regular particle counterpart, but they have opposite charge and opposite spin. So an antiproton is negative with opposite spin of a proton. To address that in terms of symbols, we're going to have P for the symbol for a proton and P with a bar over the top for the symbol of an antiproton. So let's look at a neutron. A neutron symbol is N. An antineutron is N bar. What's the difference? Well, neutrons have zero charge, so there's no opposite charge to worry about. The only difference between a neutron and an antineutron then is its magnetic spin. An electron, similar. We have E, and then we have E bar. E would be the symbol for the electron, which is a negatively charged, really tiny particle. And then an anti-electron is a positively charged, really tiny particle. Anti-electrons, by the way, are also known as positrons. All right, let's open this up into the entire classification of the standard model. The standard model is still just getting finished and complete. They're still finding predicted particles. Currently in the headlines over the last year or two in terms of the science world is this whole thing about the Higgs boson, which is also known as like the God particle, and there's all kinds of stuff with the Higgs, and I'll talk about that in class as well. Pretty cool. What's interesting about the Higgs is it was predicted to exist as a result of the Standard Model. So the Standard Model said, hey, this Higgs thing should exist. Let's look for it. I'll talk more about that in class. This is the tip of the iceberg. There's so much more to learn about the Standard Model than I can possibly go into. So all I want to do is take a moment to talk about some rules and some ways to organize your work. Let's talk about classification of matter, and this is inside the New York State reference tables. All matter can get broken up into two classifications. We have your hadrons and your leptons. I'll come back to what those are in a second. All hadrons can get broken up into baryons and mesons. All of your baryons are any combination of three quarks that makes a whole charge. All of your mesons are a combination of a quark and an antiquark that also creates a whole charge. I'll come back to that with examples in a second. Let's define hadrons a little further. Hadrons are any particle that'll interact with all four fundamental forces of nature. So not only is gravity and EM going to affect it, but so will the weak and nuclear force. Meaning, these are all particles that are found in the nucleus. Protons and neutrons are hadrons. Why do they need to be in the nucleus? Well, because the strong nuclear force only affects particles in the nucleus. That means all leptons are any particle that's not in the nucleus, which means they will not interact with a strong nuclear force. They will interact with EM and gravity, and they will also have the ability to interact with a weak force. And that has to do with decay. Again, it's really not going to come into play too often. So examples of leptons that you may have heard of are electrons, positrons, and neutrinos. You probably have no idea what a neutrino is, but you may have heard of it before. And like I said before, positrons are just anti-electrons. Another interesting thing about leptons is they're fundamental. That means there's nothing believed to make them up. Fundamental doesn't mean it's the smallest possible thing in the universe. It means nothing else is inside of it. So for example, electrons are believed to be fundamental, meaning there's nothing inside the electron. We can't crack it open and find more particles. Whereas hadrons are made up of stuff. They're not fundamental. It's believed that protons are made up of 3 different quarks. Well, what the heck is a quark? I have no idea. I don't think anyone really does. Hasn't been discovered in terms of outright handling quarks. You can't see quarks. You will never isolate quarks. They're believed to exist based off of indirect evidence, especially through some stuff through particle smashers. But really, quarks are just the name that scientists came up with for the things that are fundamental inside of the other subatomic particles. I know, it's hard to accept, but you'd have to explore the Standard Model so much deeper to even have a better idea of what a quark is. You can't visualize a quark. I can't draw a quark for you. But I can help try to define it a little bit more. And a quark is basically anything that will come together in incremental units of charge to make whole numbers of charge, either forming a proton, neutron, etc., or more or less forming baryons and mesons. Baryons themselves need to be made up of 3 quarks that come together to give a value of 0, 1, or -1 charge. You can't have -1/3 of charge. You're not going to have -2 of charge. You're going to have them combined together into 0, 1, or -1. I know this seems all very complex and overwhelming. When we go through some examples, I think it's going to make more sense. If we look at the breakdown in your Standard Model, we've got 2 main sections. You've got your quarks and you've got your leptons. These 12 particles are believed to be the fundamental particles of the universe. It quite literally is saying that everything in the universe is made up of some combination of either quarks or leptons. So, if you really want to define things, there are 12 particles that make up everything, and here they are. You've got 6 quarks and 6 leptons. Your quarks have some interesting names. This is, I believe, because physicists were trying to be funny here, and it doesn't really represent what they look like. They're the up, charm, top, down, strange, and bottom quarks. Your leptons also have relatively interesting names. You have your electron that we know of. That's one of the 12 fundamental particles. But then you got things like muons, tau, and then you've got these weird neutrinos. An electron neutrino, a muon neutrino, and a tau neutrino. You're not going to really understand what these things are. I don't even know what they are. All I know is they're little fundamental particles that make up the universe. I could try to explain it a little bit more than that, but I'll be lying to you more or less. Really, they're very difficult to wrap your brain about because it's not like you've ever seen a muon before. That said, if you look underneath each of these words, you'll see the symbol U, C, T, D, S, and B for up, charm, top, down, strange, and bottom. And then you also see the charge in which they carry. Like an up quark carries plus 2/3 electron charge, or plus 2/3 of an elementary charge. So it's not a whole charge all the way down the line. Strange is negative 1/3 of an elementary charge. Whereas lepton, same thing. An electron is negative 1e. A neutrino are neutral. Not only are there 12 fundamental particles, but then there are also the antiparticle associations. So there are 12 antiparticles. All right, let's go through some examples. Look at this. A proton is made up of up, up, and down. So a proton is made up of 3 quarks, up, up, and down. If it's made up of 3 quarks, we know protons must be baryons. Not only that, we can figure out the charge. Well, what's the charge of an up quark? Well, an up quark has a positive 2/3. What's the charge of a down quark? That's negative 1/3. So a proton is plus 2/3, plus 2/3, and negative 1/3. That turns out to be plus 1e. And that should make sense. You should agree with that because we already know protons are plus 1e. That doesn't mean all plus 1 elementary charges are protons. It just means that protons are made up of up, up, down that happen to make an overall charge of plus 1e. For example, we could have also combined up, up, and strange. I don't know what that means. I don't know what particle this is, up, up, strange, but I do know that it ends up being plus 2/3, plus 2/3, minus 1/3. It ends up making a plus 1 elementary charge. Up, up, strange is not a proton, but this subatomic particle, if it exists, has a plus 1 elementary charge. Let's think of things that could be possibly neutral. How can we make it so the 3 come together to give a 0 charge? Well, let's look at these. We're going to combine 3 quarks to make an overall charge of 0 elementary charge. Maybe up, down, down. Let's see what that does. What does up, down, down make? Up, down, down is positive 2/3, minus 1/3, minus 1/3. That's an overall charge of 0. That's a possibly neutral object. Maybe this is a neutron. Again, I don't know. But I know neutrons are neutral. And this is neutral, so it's possibly a neutron. And we can go along the line. We can make a bunch of negative. What if I have a down, down, strange combination of quarks? Down, down, strange would be negative 1/3, negative 1/3, negative 1/3. Yep, that's negative 1e. That's possible. These are all possible combination of quarks. Let's think of some that are not possible. Could we have an up, up, up quark? Well, up, up, up would be 2/3 plus 2/3 plus 2/3. That's 6/3 or 2. Well, having a combination of 2 charges isn't impossible. It is not within this rule of 0, 1, or negative 1. So while mathematically it's possible, physically it's not. We will not have an up, up, up combination. As long as it's a 3 quark combination that ends up with a charge of 0, 1, and negative 1, it's a possible subatomic particle. Lastly, I want to talk about these mesons here, quarks and antiquarks. What if we have an up, anti-up? What does that end up equaling? Well, we have 2/3 plus, well, what's the charge of anti-up? Remember, antiparticles are opposite in charge of the non-antiparticle components. So if up is plus 2/3, then anti-up is negative 2/3. plus 2/3, minus 2/3, this gives us an overall value of 0. This is possible because, remember, it still needs to suffice that rule of 0, 1, or -1. And it did. Good to go. Is an up anti-down possible? Let's see. Up, anti-down. 2/3, anti-down. Well, down is -1/3. Anti means it's plus 1/3. Yeah, I think this could be possible. This is one elementary charge. It's a positive subatomic particle. I have no idea what subatomic particle could possibly be made up of up anti-down, but I know that it's within these rules. Seems very overwhelming. We're going to go over plenty of examples in class. I think it's going to be a little bit more clear. The last one I want to give you is simply maybe an anti-proton. So let's look at up, up, down. This is the last example I'm going to give. Remember, up, up, down ended up being 2/3, 2/3, and -1/3, giving us overall +1. Well, anti-up, anti-up, anti-down will be -2/3, -2/3, and +1/3, giving us an overall -1e, which should make sense because this is an antiproton, which is the same as a proton but negative. I know, it seems overwhelming, and it's really weird and very strange, but I will hopefully spin you around and bring it back to the top in class. Thank you.